Okay, so it's a great pleasure to have today with us Barbora Adamcova, who is visiting us since Monday, today. Barbora received her PhD, no, not yet, so her bachelor's degree from the Czech University in Prague. Then she received her master's from the same university and working at the Astronomical Institute in the Czech Academy of Sciences. And now, since last year, she's pursuing her PhD at the Astronomical Institute of the Czech Academy of Sciences, working with Gini Svoboda on blueberries, green peas, and various other vegetables, fruits, and so on. So Barbora will talk to us about her latest results from X-ray observations of blueberries. So Barbora?
Yes.
Okay.
So hello, nice to meet you. Thank you for having me here. So as Andreas mentioned, I'm mainly working in the Astronomical Institute of the Czech Academy of Sciences. And I'm sorry about the meeting is being recorded. I can't see my cursor, so I don't know how to turn it off. So probably we'll have to do with it. And I'm also collaborating with Andreas and Elias here on some of the results. So first, let's look at why we are even talking about star-forming dwarf galaxies. You have the very nice image here, which is very famous. I think most of you or all of you have probably seen it. And what I'm interested in is the era of reionization, which is where the first stars and the first galaxies started to form, and where the light became once again, or the universe became once again not opaque for the light, because there were the dark ages, and then the first galaxies came, and the light from them, the ionized radiation, helped reionize the neutral hydrogen. And this is very important part of the galactic history, which can tell us something about the galaxy evolution, the chemical enrichment. And dwarf galaxies were the most dominant type in that era. Dwarf galaxies especially are very important for the era of reionization also, because if you can notice here, this is a Haro 11 as an example. Most of the dwarf galaxies are very irregular. They're not like the big elliptical galaxies, which are very symmetrical. And these are ideal for leaking the ionizing radiation, which is the Lyman continuum photons, which are very high energy UV light, which is capable of ionizing the hydrogen. But it's like the star-forming dwarf galaxies are the only ones capable of ionizing the universe, the hydrogen, or not. One of the other possible sources, the second possible source of ionizing radiation, is also the active galactic nuclei, which is the AGNs, like the very bright sources. Were observed first as quasars. And you can see here the also very famous AGN model. For example, the accretion rate, because there's like a black hole in the center, there's a accretion onto the supermassive black hole, and that can give us like great amounts of, for example, the X-ray radiation, or they can emit across the electromagnetic spectra. Some of the galaxies, like the AGNs, can be radio quiet as well, but mostly they emit in all the spectral ranges. And their UV light, if they emit, like if they were, for example, in the era of ionization, they would emit a lot of deionizing radiation, which would be more effective than the star-forming dwarf galaxies. But of course, there is a question if they were there or not, and how it's looking. So, for example, let's look at what did the James Webb Telescope reveal, because now we can observe the galaxies which were really there in the era of reionization. We don't have to only observe the lethal universe, but we can look into very high redshift. For example, even at the redshift of 8, which is the era of reionization redshift. And there have been a lot of the dwarf star-forming low metallicity galaxies, as I have mentioned, that we are interested in them. And what is also interesting is a fairly new observed the population of galaxies, which are the little red dots, which are found more numerously at higher redshift. So what is quite interesting about them is that in the local universe, we might have a few analogues, but we don't really observe them in the nearby universe. But the farther you go with redshift, so at redshift 4.5 or 8, like it's becoming more and more numerous, which is something we don't see with quasars. And that's one of the big questions nowadays. And what is interesting about these galaxies is that they're extremely compact. But there have been studies, for example, by Green et al., that 80% of the little red dots they observed had broad Balmer lines, which can be suggestive of having an AGN. But there's also some problems because they show flat infrared spectra, and there's also no X-ray detection. There has been deep field Chandra observations, and those galaxies don't have significant X-ray fluxes. They were rather underluminous. So it's a question, what are these? So this is also one of the reasons that we don't really know yet, which is like the most important ionizing source of radiation in the era of reionization. So what can we do, or like how can we look at these galaxies to understand it better? What would be best is the multi-wavelength observations, because as you can see, this is like the starburst of like star-forming galaxy spectra, and this is the gray, and in the colored lines is the like active galactic nuclei AGN spectra. And you can see that they differ in quite a few parts. For example, if the AGN is radio loud, it has some flux in the radio, but for a normal star-forming galaxy, it's quite low. Or if you have a UV bump right here, it's quite also like, okay, we have an AGN. So it would be best, or with X-rays, which mainly I'm working with, if you have a high X-ray flux, it's often like the only explanation will be AGN or maybe some ULX, like ultraluminous X-ray source. But that's also a question, and it would be the best if we could have each of these measurements to really understand what's happening in the galaxy, if it's just a very bright star-forming galaxy or if it could be an AGN. So how would we do it? Because for the very high redshift galaxies, it's quite difficult because we would need very high exposure times. For example, for X-rays, it already takes a lot of time to observe the galaxies in our near universe, especially if they're dwarf galaxies. But of course, it's much better to observe the local analogues to have everything in detail rather than for the high redshift dwarf galaxies. Because if we observe a galaxy with James Webb Telescope, we observe the infrared light, but it's rest frame optical or UV spectra. So we don't have all of the information. So this is why we are mostly focusing on the local analogues, which are the dwarf star-forming galaxies in our nearby universe. Here you can see a table just to see the comparison that, of course, the high redshift dwarf like galaxies or sources are much more extreme than the local analogues. So can we find some better local analogues, or do we just focus on that? So let me tell you, now I'm thinking if you can see, if I'm standing here, if you can see the screen. Is it okay? Okay, good. So what I study mostly, or we study, are the Greenpeas and Blueberries, which are much better local analogues for these high redshift galaxies. And you can see, well, you can probably guess that the green is the green pea and blueberry is the blue galaxy. And unfortunately, there's the line, but why the colors are like so is that both of these the populations of galaxies have very bright O3 5007 emission line, which in the SDSS filters because of their red. So the green peas are on redshift 0.2 to 0.3, and the blueberries are on redshift smaller than 0.1. So the O3 line falls into the R filter for the green piece, and in the G filter in for the blueberry. So that's why we see these very characteristic colors. And let's look at the green piece. So they are very compact, low mass, and highly star-forming sources. This is like the average, let's say, or like approximate, like some tens of solar masses per year is their star formation rates. The redshift I've already mentioned, it's 0.2 to 0.3. And they have been observed first, or like they have been first discovered by the Cardamone paper, which is like uses the Galaxies when people who are not doing astrophysics were noticing little like compact green galaxies. That's how they've been find out, which is also quite interesting. And they have the UV Lyman alpha lines, as I have mentioned, that there's a ionization by the Lyman continuum photons. Basically, then you can see, if it happens, you can see the Lyman alpha emitted. So a few of the green peas are actually confirmed as Lyman alpha leakers, which is one of the reasons why they're also quite important for the studies for the epoch of reionization era. And they have no clear AGN signatures in optical or UV. And their spectra is similar to the high redshifted galaxies, as I have mentioned, that were observed by the James Webb Telescope. For example, these are 3 epoch of reionization galaxies and 1 green pea galaxy. Of course, the spectra from James Webb is not that detailed, but I think it's quite visible that they're quite similar. And there, for example, the Scherer et al., the Rhodes paper, do say that the green pea galaxies are quite good local analogues to the epoch of reionization galaxies, or with the little red dots. This is not that sure, but there have been some comparisons also with the little red dots, but there's also a problem with how the little red dots are defined, because they have to be very, very compact, and the green peas don't have to be as compact as them. So that's up to a debate. And now let's look at the blueberries. This is what mostly I work on, which are even the more local analogs to the green peas, let's say. They have the same very high O3 ionization line, emission line, sorry, and they have high ionization ratios. And they're similar to GPs, but they're more extreme. So they have lower metallicities, about 8, and they have lower stellar masses. And they're quite unique in the sense that they have very high specific star formation rates, which is the star formation rate scaled by mass. So like if you have a galaxy or 2 galaxies with the same star formation, it's more significant for a galaxy which has a lower mass. And now let's look at how the green peas first to look in X-rays. So how can we study it? So in the X-ray emission in a star-forming galaxy mostly comes from the high and low mass X-ray binaries and from hot ionized gas. Mostly for star-forming galaxies, which have higher star formation rates, it comes from the high mass X-ray binaries. And you can there's been some studies that give us empirical relations, how it should look on there's the X-ray luminosity, and there's basically it just takes into account the star formation rate and the metallicity, which is like the exact numbers are not that important, but we have an empirical line where the galaxies should lie if they're purely star forming. And what has been done is that so we had the observations of the green pea galaxy, of 3 green pea galaxies, which you can see in green here, and one of them is only an upper limit, which is the green pea 3, but 2 of those galaxies are higher than the empirical relation. So also just to say that the yellow points are thought to be AGNs. So they are in the similar part of the plots. Let's say the luminosities here are 10 to like the 42. So it's quite high for a normal star-forming galaxy. So there has been, so they have been thought to be AGN candidates. But of course, it's not very simple to say just from one observation, from one X-ray observation. So yeah, so there has been new star observations of the two green peas, because that the original observations here come from XMM Newton, but there have been also observations, they have also observed with new star, and there was no significant hard X-ray flux, which is quite interesting also, because for an AGN you would mostly expect there to be hard X-ray flux, but it depends on the galaxy, and if it's a dwarf galaxy, it's also not as simple. But they have some other, for example, Weiss color diagrams show that it could be an AGN, or they have higher mid-infrared luminosity. So it's quite inconclusive in this sense. And now we have, or there have been, for the GP2, so the one right there, there's a, well, confirmed AGN. It's, I myself would not say it's 100% sure, but it's very, very likely that it is an AGN, because when you have two, basically we have observations for two epochs from 2 years, and they show clear X-ray variability. So for the hard X-ray luminosity, it stays constant, and the X-ray luminosity drops by 60%. The spectral slope also becomes much harder, and the hardness of the X-ray slope could be like hinting at some obscuration events, for example, which is what we think happened here, or is happening there. So like the variability measurements are quite important for these galaxies. If we can have more observations in different epochs, it could also help us to see if a galaxy is an AGN or if it's just a star-forming galaxy. Yeah, this is just the obscured AGN model explains the soft X-ray suppression via basically the column density increase. So this is a fit of both of the epochs, simultaneous fit of both of the epochs, taking into account the change in column density. So this is also one of the things that we can do for dwarf galaxies. And what about Blueberries? So this is what I've been collaborating on here with people from here. This is a similar plot to what I showed you before. It's just a bit less simple in the sense that here now on the y-axis we don't have only the X-ray luminosity, but we also have it scaled by the star formation rate, and here now is the metallicity. And we have the 3 green pea galaxies that I showed you before, but we also have now 7 blueberry galaxies. And most of the galaxies that have been observed was actually not detected. So only 2 blueberry galaxies have been detected by XMM Newton. And the exposure times were set to measure the galaxies if the star formation, if the X-ray flux is coming from the star formation rate. So they should have been safely detected. As you can see, they are mostly not. For the BB8 right here, it's again higher than the empirical relations. And the BB1 is actually below the relation. And for the rest, there was no detection. No, we only have the upper limits, and some of the upper limits are really extremely low. So the bars here, so there has been a stochastic simulation done that show essentially the confidence interval in which the galaxy is coming from, the X-rays coming from the normal high mass X-ray binary distributions. And for example, you can see for BB4 and BB3, it's almost more than 99.9% sure that it cannot be, these values cannot be explained by the scatter or the stochasticity of the fluxes. And one of the reasons that could be happening is that the blueberries might not be old enough to give rise to significant X-ray binary population. They would have to be very young, though, with like less than 5 mega years. So it's we don't know what's happening for now and like why, and we're trying to find it out. And let's just quickly also look at the radio observations, because the blueberries and the green peas are behaving very similarly, like in X-rays. So again, for the radio flux, it's a similar plot as we have for the green peas or for the blueberries. Just in this case, the radio is coming from star formation activity, or there can be an AGN, for example, but of course, we have to keep in mind that if there's no detection or if the radio flux or emission is quite low, it does not mean there's no AGN, for example, because the galaxy can be radio quiet. And yes, you can see that there's only this is archival observations for GP1 and for some other green peas and for blueberries, only 2 were observed, and most are upper limits or have not been observed. The field of view have not been observed. So this is also quite interesting because most of these lie below the relations. And this is again coming from the empirical relations are again coming from the star formation rate. So if the star formation rates, of course, are measured right, we should see all of these around these empirical lines or relations. And we have also done new observations with VLA of GP1 and GP2 and actually GP3, but that one was not detected. For GP1 and GP2, they look to be in line like with the star formation activity. So they look star forming in radio. There's no excess flux for GP1 or GP2. So we measured the index, and it looks to be again for like synchrotron emission, which could be star formation or AGN. So taking into account that there has been the variability for GP2, the X-ray variability, it's fairly interesting to see that, for example, in radio, we cannot see much, but again, no or like lower emission in radio does not mean there cannot be an AGN. So I would just like to quickly say that in this way, for the dwarf galaxies, it's kind of a diagnostic puzzle in a way, because we have all of these diagnostics that we can use, but there can be, for example, probably most of you know the optical emission line diagnostics, the BPT diagram, which if there will be time and you will be interested, for example, the GP2 is in the star forming region of the plot, which again is quite interesting because it should be a star forming galaxy. It should be a very very intense starburst. But we have the other points that there's X-ray variability. So which is how is it called? Sorry, which is consistent with an X-ray with an obscuration event in the AGN. For the X-ray observations, they're quite sensitive to AGNs, but it truly requires deep exposures. Like I said, even for the dwarf galaxies in the nearest universe, it takes quite a long time to measure them properly, and it would be better to have the multi-epoch observations. For radio, again, it can differ, and for mid-infrared diagnostics, it can be quite problematic, but I'm not an expert for that. And this is a very interesting paper. If you're interested in diagnostics for AGNs in dwarf galaxies, is basically how the different diagnostics overlap with each other. So this is probably the most used and known one, which is the optical, the emission line diagnostics, the BPT. The BPT selected galaxies. So you can see from this plot that not all galaxies that have been selected by BPT have been selected by the other diagnostics. So this is also why we think it's very important to have multi-wavelength observations, especially for the dwarf galaxies, which are very, very compact and very small, and you need to be very careful to see or to say like what is exactly happening in the galaxy. And yes, so maybe for the final takeaways and outlook, I will just say again that the star-forming dwarf galaxies are very important for galaxy evolution and for how we understand how the epoch of reionization era happened. And we now see a lot of new observations from James Webb that tell us something about how the galaxies work or how they might look. And we can use the local analogues, especially the green peas or the blueberries in our case, to help us study the high redshift sources in detail. And based on the new X-ray and radio observations, we can identify new AGNs, and we have done it especially or at least for one of the green peas. And for the blueberries, they're mostly X-ray underluminous, so it would be very interesting to see that how it really works, if there can be AGNs that are hidden in these galaxies. For example, for the BB8, but it's a big question. I would not say it's an AGN for sure, of course. And now we have new excellent Newton blueberry galaxy observations. So we're now working on seeing how these look. And yes, I think if that will be all from me. And if you have any questions, feel free to ask.
Could you please go back to your slide where you had metallicity on the bottom?
Yes.
That's it.
Yes.
I see segregation. The green peas are on the right, higher metallicity.
Yes.
Okay. Is there a reason for that? Or could it be that small number statistics? You only have 3 of one.
Yes.
And a few of the others. And I see one is overlapping. So
yes.
well, are they indeed 2 separate groups, or they could come together?
Yes, that's a very good question, because I mean some teams have like green peas that can be on the lower redshifts, but we decided to just use maybe I can go back here. So there have been 2 papers like separating them as like separate groups of green peas and blueberries, because the blueberries are on the, let's say, in the nearer universe, and they do indeed have lower metallicities on average. But it also can, I guess we can look at it in the sense that these both could be called green peas. I guess that's just a way of how to define this. But yes, like if you go, or even if you call all of this green peas and you go to the nearer universe, they have lower metallicities on average. Like if you put basically the blueberries.
Do I understand why?
Yeah. I don't, but yeah, it's if you basically use the same criteria as for the green peas and you use it on lower redshift universe, you get more extreme metallicities and stellar masses. But that's a very good question.
That's something related. Is there any sorry, but it's exactly related. So is there any chance that the metallicities of green peas are overestimated if they have an AGN? Because if they have an AGN, the high excitation lines, like the nitrogen 2 and O3 that are used for as metallicity indicators, are going to be stronger than in star-forming galaxies, and the metallicity indicators have been calibrated for star formation, for star-forming galaxies.
Yes.
So is there any chance that there may seem to be artificially higher metallicity because of a far excitation? Or in other words, if the metallicities are not based on the electron temperature calibrated metallicity indicator, then is there any chance that they're biased?
That depends on whether most of the green peas have an AGN. I mean, I would not say that because, for example, we have observed 3 green peas, and I would say that by chance we found 2 that might have an AGN. For green P2, we're like, it's more probable it has an AGN from what we've done, but for the GP3, again, it's only an upper limit. And for a lot of the green peas that have been observed in some archival data, it does not look like they have very big fluxes. But of course, it would be much better to see maybe a big population of the green peas to see if, I don't know, 9 out of 10 has a probability of hosting an AGN. And then, yes, maybe that could be one of the reasons. But unfortunately, I don't know that. It would be very interesting to know.
It's an interesting question.
Yeah, could be.
If green pea, if assuming that the green pea has an AGN, but is not that strong AGN, would you expect a big bias on the ionization lines that the metallicity calculations are calculated?
It would be the same bias that you would have if you measure a metallicity in a typical star-forming galaxy versus in an extreme star-forming galaxy that has extremely young stellar populations, because the UV is harder, so it produces high excitation lines. So that's why the electron temperature-based metallicities are more accurate, because they do account for these effects.
Yeah, my question is if we can't see the difference if the AGN is low in those spaces.
You cannot, but we'll reflect the metallicities. We'll affect the metallicities. But yeah, so
Okay, thanks for this presentation. Could you go back to the same plot?
Yes. Sorry. Here, yes.
Yeah, okay, so I was curious about the last point that you made there, and you say that this X-ray non-detections could be due to these galaxies not having all the populations.
Yes.
So that would make them very young.
Yes.
So I was wondering if is this consistent with the whole structure formation?
That's a good question. I mean, as I mentioned, the blueberries have very high specific star formation rate. So that's kind of hinting to us that they could be very, very young. So they're I don't know, I don't think I have the plot here, but basically if you have something like this, like a x-axis, you would have the blueberries on the very high specific star formation part, which is consistent with them being very young.
Okay, thanks. Can you quantify this based on the fact that you don't see an X-ray emission, based on the how?
Yeah, I mean, it would be very interesting to get the the population histories for them, but I don't think we can say just because of the flux and because they are high on the specific star formation.
Thank you.
Another question. Christina, about the AGN metallicity. I mean, here is the metallicity right on the x-axis, and you can see that GP2 and GP3 have more or less same metallicity. But if you go back to the other plot,
yes,
the one of this one,
yes,
you can see that GP3 is an upper limit, so it's okay, it's an upper limit, but you can see that the luminosity is very different, though they share the same metallicity. Like it might be that GP2 is an AGM, even if we are not sure, and GP3 it is not, since there is an upper limit, but they share though the same metallicity. I don't know if I make a
The other
point.
plot is LX per star formation rate in the y-axis.
Yes, but this doesn't say if it's an, I mean, the y-axis doesn't express if it's an AGN or not. Like, what does the y-axis is telling us? Like, it's not computing the AGN contribution or not? Or did I understand wrong?
No, this is just the y-axis here is it's just the X-ray luminosity.
Yeah.
And here again, it's just an X-ray luminosity, but filled by the star formation rate. But these bars basically, it doesn't like tell you the contribution of AGN, but it tells us like how probable it is that the fluxes that we're seeing are caused like by the or like can be within or how to say this better, like essentially if you have the empirical relations and you have the X-ray luminosity functions that are usual for a galaxy, like if it is probable that it's like within the scatter of those. So if we have a galaxy that is completely like out of bounds, it means there's like a big chance, like almost 100%, was like higher than 99.9, which are like the yellow boxes, that it cannot be explained by the scatter. So there has to be something else happening there,
Yeah,
if that makes sense.
yeah, but, okay, maybe it was not clear.
Yeah, sorry.
No, not because, oh, yes,
Uh-huh.
I wanted to say that in this plot, I don't care about the y-axis.
Okay.
I care about only the metallicity.
Ah, okay.
And GP2 and GP3.
Okay, yes.
Apparently, they share the same metallicity.
Yes.
But if you go back to the other plot.
Yes.
It's only X-ray luminosity.
Yes.
You can see that the GP2 and GP3 are
Yes.
in a very different place.
Yes, like you
So-
mean on the x-axis.
On the y-axis.
The y-axis.
Yes. So.
Yes, because it's not scaled by the, I mean, it's basically how to,
Yeah, but I wanted to say that
Yes.
maybe the AGN is not affecting the metallicity like Andreas was saying. Because from this plot, it looks like just looking at the y-axis, that GP1 and GP2 might be arbor and AGN, while GP3 not.
yes.
The X-ray luminosity of an AGN can be anything. I mean, you can take an AGN, a low luminosity AGN can be anything from 10 to the 39 up to 10 to the 41, 10 to the 42, can be orders of magnitude. There isn't a fixed relation, a fixed scaling between X-ray luminosity and any other property. There's a huge scatter.
Oh, okay.
So, and that's why it's a problem.
Okay.
Cannot really say much.
Okay, thank you.
Yeah, maybe it's
There is only the difference is less than an order of magnitude between the GP1, GP2, and GP3.
Yes, that's.
Well, it could be more, depending on where the upper limit falls.
In the GP3, that the first detection of the variability in X-ray is
you mean GP2.
GP2 or GP3.
GP2, yes.
Have you tried any other, like an SCD fitting,
Yes, I think
counting for AGN contribution, for example, to confirm if there is an AGN and independent confirmation?
honestly, I'm not sure now. Mostly Peter was working on it, but yeah.
So the conclusion is based on the
Mostly this, yes. The variability and yes, the obscuration scenario, which is consistent with the column density increasing from the epoch to epoch by this much.
Okay, there are no more questions then. Yeah, thanks so much.